Hello, Mr. Ryan, right? Yeah, so today we're going to talk about an interesting math problem. Pivot integer. What's a pivot?
You pivot in.
What's
Is
this
it
one?
like the sports thing, like how you pivot like in netball?
Yeah, kind of. Pivot is, what's this word in English?
I don't know how to.
Explain it, right? Remember, when we talk about a quick sort, how do we solve these numbers? Quick sort?
Pivot. 1, 2, 3.
Yeah?
1, 2,
Pivot.
3,
Well, first of all, we
4,
choose the pivot index. Let's make it 5, okay? Let's choose the last element as the pivot integer. So what do we do with the quick sort?
9? What if it's 9?
Okay, just 5, okay, for now. So how do we use the quick sort? Remember 5. What numbers are smaller than 5 here?
1, 2, and 3.
Okay, so 3, 2, 1. Okay, this is on the left hand side, 5 here. What numbers are bigger than 5?
9 and 7.
9 and 7. We can solve these two recursively. Right? What's the pivot number? Let's pick one, okay? Or pick 2. You know, pivot number does not have to be a particular index. We can randomly pick any index, right? Or we pick these 2. So we pick these 2. What's the number smaller than 2? 1.
1.
What's the number bigger than 2? 3. Each individual number is sorted, right? And then 5. Okay, so now we pick 7. What's the number bigger than 7? 9. What's the number smaller than 7? Nothing. Okay. And now look, it's sorted, right? Yeah, this is quick sort. Remember, we randomly choose an integer
What if it's
as
9?
a pivot.
What if it's. What
Yeah, that's a duplicate. It's the same. So the idea of the quick sort, remember we talked about in early days. We pick a number and we find out the numbers that are smaller than it, and we find out the numbers bigger than it, and we recursively sort the left and right part. Okay, this is what the pivot is for. Okay, so not today. Pivot is different. Consider, look, 1, 2, 3, 4, 5,
6,
n. Here n. N is the integer number. Okay. So let's say here 8. Okay, n equals 8. So we want to find this integer, pivot integer x. So 1 plus 2 plus 3 plus x equals x plus 1 plus x plus 2 till n. Okay? For example, till 8. So what number?
Why is it x plus 1?
This is the next number. So we want to find out, for example,
Yeah, but you said 1 plus 2 plus 3 plus equals.
till x.
Yeah.
What? Look. 1,
Yeah,
2, 3, 4, 5, 6, 7, 8. Okay, so n equals.
What's the difference between n and x?
That's a good point. We want to find out the x. If there's an x, look, n equals 8, right? So can you find an x between if x equals this? So 1 plus 2 plus 3 plus 4 equals 10, right?
How do you
4 plus 5 plus 6 plus 7 plus 8, it's not equal 10, right? So we want to move this x to the left or to the right. So that,
What if x is n?
good point. There's only one case is when x equals n, then it satisfies this. Okay, so basically n equals 1, then look, there's only one number. So the left part and the right part equals 1, okay? This one, if we move the x, look, this is a cursor, right? Okay, we can move left or right. Let's move it to the right. Here. One x is here. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals what?
How do you know if 1 plus 2 plus 3 plus 4 is 10?
You tell me. How do we know 1 plus 2 plus 3 plus 4 equals 10? You know how to solve it, right?
Yeah.
Okay.
Then why doesn't then does the computer know it then?
That's a good point. You tell me later, okay? Do you understand this question so far?
Yeah.
Okay, so 1x equals 6. What's the sum of this one? What's the sum?
1 add 2 add 3 add 4 add 5 add 6 equals 21, right?
21, okay? What's the sum of this part?
6 add 7 add 8. 21.
21. Okay, so we found it. X equals 6. It's satisfied. Okay? But if n equals 4, 1, 2, 3, 4, can we find such number, x, so it's satisfied, the left part and the right part? Look, this x is counted as boundary, okay?
You
So-
don't have to use plus the x. It doesn't matter because you can just do 1 plus 2 plus 3 plus 4 plus 5 and is equal to 7 plus 8.
That's a good observation, yes. That's a good observation, yes, you're right. Okay, because they all plus this one number, okay? Yeah, that's a trick.
A trick.
Okay, so coming back to this one. 1 plus 2 plus 3 plus 4. Can we find such number x that the left part the sum of the left part equals the sum of the right part? No, right?
No.
Right? Okay, so basically this is the question today. Any source? I mean, this is very simple question.
Bruteforce.
Brute force. How do we brute force? We basically check. We just check x, right? Yeah. Because look, you're given this n, right? You're given this n. How many possibilities we need to check?
N.
N, obviously, because there are only n choice. Alright? Okay, so I'm going to write down the brute force. You tell me the time complexity and how do we improve it, okay? Okay.
Yo.
Okay, what's this?
It's my sock.
Okay. But you understand this question pretty well, right? When n equals 1, the answer is 1, right? When n equals 1, obviously there's one number, so x equals 1. So the left part is 1, the right part is 1, okay? So how do we brute force?
Checking every possibility.
For I in range start from 1 to n plus 1, to n inclusive, okay? The left part, okay, let's call it A. The sum of the left part, we use the sum function, right? Sum the left part, range start with 1 to I plus 1. The right part, sum range start from I, right? I inclusive to n plus 1, right? And then if A equal B, return I. Otherwise, return minus 1, right? Look, simple brute force. Am I right? Simple.
Easy.
So easy. Exactly. Okay, so how can we improve it? I mean, by the way, this can be written in one line using the next function. Return next I for I in range 1 till I plus 1. If sum of this bit equals sum of this bit, right? And by default is minus 1, right? If we can't find it, okay?
Why aren't you writing the I part?
Sorry, which one?
Why aren't you writing the I part?
Yeah, too squishy. But look, next function, remember we talked about? Next one, this is the iterator. We want to find the first element in the iterator, I, for I in range 1 till n plus 1, n inclusive. If A equals B, if sum of the first bit, left part equal the sum of the right bit, right? If we can't find it, the minus 1 is the default value if this iterator is empty, okay? Okay, so what's the problem of this one? What's the time complexity? This is On, but what's this bit? On squared, right? Look, this is On. This is On, right? There's a loop inside, there are two loops. These two, On, right? On. Inside the loop is On squared, right? On squared, that's too slow. So you're saying 1 plus 2 plus 3 plus 4 plus n. Do we know how to solve this? Like the sum. And when n equals 100. Okay. When n equals 100, what's the sum?
It is 50-50.
50-50. Okay, so we know the mathematics equations to solve that, right? Okay, before coming to this, we can also use the prefix sum. We can calculate the total sum here, right? Total sum equals sum of everything, right? Sum from 1 to the n plus 1, right? And then we can have a prefix sum, the left part, A equals 0, A plus equal I, okay? So I'm telling you, okay, this total sum is total. The left sum is A. What's the sum of the right part? This sum is A.
Total minus A.
Look, this is I, right? This is I. Here. The current sum is...
Is I in A or is...
In A. Okay, so what's the sum of this bit? Look, this bit...
Wait.
Actually.
Is I...
I.
Is I A?
Look, because look, we talk about I is inclusive in both left part and right part, right? So this left part is A. So the right bit, the green bit is total minus A plus I, right? Yes?
Yes.
Okay, so look, this is On. If we do this, On, and then we can do this A plus equals I. This is accumulate prefix sum. And then we can use the simple math to calculate the sum of B. So instead of B equals that, we use this, right? Yeah? And instead of this one, we use A plus equals I. Every time we accumulate this sum. So what's the time complexity after this improvement?
O-N.
O-N, exactly. This is O-N and this is O-1. Okay? Well done. Okay. Prefix sum, yeah, we can use the prefix sum like this way, or we can do this accumulate, right? It's the same thing, yeah? Accumulate function we talk about, right? Accumulate, right? It's the same. Okay. This is a great improvement. We can do better. Binary search, remember? We pick the middle. If I can calculate the left bit, And if the left bit, the sum of the left bit is smaller than the right bit, so how do we move it? If the sum of A is smaller than sum of B, if the sum of the left part is smaller than the sum of the right part, so what do we move to? We cut into half, right? This is the I. This is the left boundary, R boundary. Then this is the middle. And I'm telling you, okay, now the sum of A, this bit A, is smaller than this bit B. So where do we move? Move the middle. Where do we cut into half to solve? Remember the binary search? I have a number in my mind from 0 to 100.
Right. 50.
Yeah, always cut in the middle. Okay, so now look, this is smaller. So A is smaller, so we need to move it to the right, obviously, right?
Yeah.
To increase the left bar. And the opposite. If it's too big, then we move to the left. Remember the mathematic. We talked about that in the early days using the mathematics induction. Mathematic induction, okay? So 1 plus 2 plus 3 plus till n. What's the sum of it? Sum of it, right? Sum I equals 1 to n. I, this is sum, right? Look, equals the first item plus the last item times how many items are there? N items divided by 2, okay? Yeah? This is the equation, right? And we know this equation. Obviously, we can change this. We don't need to accumulate sum. We don't need the prefix sum. We can replace this. A equals this bit. And then B equals, we can directly calculate it. Am I right? Okay, so what's the sum of 3, 4, 5, 6, 7, 8, 9? Okay, what's the sum of this? You're doing brute force?
3 and 4 and 5 and 6.
I mean, one easy way. 3 plus 9. Yeah, it has to be continuous, right? 3 plus 9, the first item plus the last item, times how many items are there? 2, 4, 6, 7, divided by 2. Okay, what's the
3
answer?
and 9 equals 12. 12 and 12 times.
Divided by 2 is 6. 6 times 7, 42.
42.
Yeah? Can we verify this? 3 plus 4, 7, 12, 18, 25, 33, 42. Okay? Yeah, you know this equation. The first item plus the last item times how many items are there? Divided by 2. Okay? So how do we interpret this? This plus this. This plus n minus 1. How many of them divided by 2? Look, remember 1 plus 2 plus 3 till 100. How do we know it's 50-50? 1 plus 100 is 101. 2 plus 99 is 101. How many pairs of that? 50 pairs of that. So 50 times 101 is 50-50. That's why we got it. Okay? Make sense? Yeah, okay. Okay, so we know these tricks to compute the sum of, of continuous, the left part and right part. We can do this binary search. Okay, binary search. How do we do binary search? And tell me that you think about the time complexity. The left is R, the right is N, right? Why left
The
boundary
L,
is more
the L
R.
is 1.
Yeah. L is 1, okay? Left is the, because 1, 2, here, N, right? Right? The left boundary at the beginning, the right boundary. The middle is L plus R divided by 2, or shifted 61, right? These two calculated first. The left part, what's the sum? 1 plus M, right? Times how many? M divided by 2, right? The right part, we know the sum, right? M plus N, right?
There's a problem here. Technical difficulty. We got a problem.
Look, this is 1, this is N, okay?
Working.
This is middle. So when we calculate this middle, this middle is just a place to represent the middle. We calculate sum. So we're not calculating this bit of sum, we're calculating the whole bit. Okay, so that's 1. 1 plus M times M divided by 2. And N plus N times how many numbers between N to N? How many numbers?
N minus M.
N
Minus M.
plus 1, right? You forgot the plus 1. Why? Look, 3 to 4, how many numbers?
0.
2. So how do we get a 2? 4 minus 3, that's 1. We need to plus 1 here. Right. Yeah?
It was 1.
Sorry?
It's 1.
Okay, and then divided by 2, right? And then look, if A equal B, obviously we return middle, right? Then if A is smaller than B, okay, so you're saying the left sum is smaller than the big sum, so we need to move it to the right, right? move it to the right. So the left equals mid plus 1. Okay, so you tell me what's next. If A is bigger than B, so what do we do here?
Move it.
Move it to the right.
Yeah, how do we move it to the right?
L equals M
R.
minus 1.
R. R equals.
M minus 1.
Yeah, and then otherwise we can't find it, return minus 1. Okay, the time complexity. What's binary search?
Log n?
Yes.
Yeah, boy.
Yeah, because every time you cut in half, you cut in half. There are 100 numbers, and every time you cut in half, how many times, maximum, how many times?
Up to 25.
Oh, log, is it log 2
to
to the
1.
power 100, So, this is the number of times. Every time you cut in half, the search space is narrowed down, okay? Oh, log n. We can do better. So this is a great improvement, okay? So how can we do better?
We can't.
Yeah, we can. Look, the left part is what? The sum of left part is 1 plus x times x divided by 2, right? This is a, right? This is a. This is x here, right?
Yeah.
And what's the sum of this bit? What's the sum of this bit? Is it equals the sum of everything minus this bit, right? Am I right?
Yeah.
So the sum minus this bit plus x. Okay, so the sum of everything is n times n plus 1 divided by 2 minus the left bit, right? Minus left bit 1 plus x times x divided by 2 plus x, right? This is 1. This is n. And we want to find if there is an x here, right? So the left bit, the sum of the left bit, this is the sum of the left bit. The sum of everything is this one, right? The sum of everything. Minus this bit. This bit minus this bit is this bit, right? But I have to plus x here, right? Plus x here, right? Okay? So let's solve this problem, okay? So, look, this one. 1 plus x times x divided by 2. This move to the left, plus 1 plus x. Yeah? And then minus x equals n plus 1 divided by 2, right? Look, these two added together. Look, half of this plus half of this equals what? Half of this plus half of this equals what? The whole, this one, right?
Yeah.
So 1 plus x times x minus x equals, this bit is the total sum, right? Total sum, okay? So what's this? Do you know how to calculate this, yeah? Yeah? So x plus x squared minus x equals s. Cancel out. So x squared equals s. So what's x? X equals square root of s. And we just have to check if this is a whole integer. So s equals n times n plus 1 divided by 2. Okay? And then square root. So x equals square root of s. If x is integer, if it's an integer, right? Then return integer part of x. Otherwise, return minus 1. What's the time complexity? You know this answer?
1.
Oh, 1, yes. Oh, 1, right? If this function, this is amortized. What's this word? Amortized.
Oh, no.
Amortized to O1, right? Because in modern computers, the processor, the CPU, computer, what's CPU? I talked about this before, CPU. This is the brain of computer. Central processing unit. The brain of computer. In brain of computer, he knows how to deal with this SQRT square root. He knows how to calculate the square root of any number very efficiently. So we treat it as this function as amortized O1, right? Look, mathematics. We just try to compute this. So which one is the fastest?
O1.
Yeah, obviously this one, right? And there's no loop. I just calculate the square root, right? How do we get this? We just prove it, right? Okay, so to sum up, the beginning, we talk about the brute force. We're just checking every possibility. But that's O1 square. And we made a slight improvement because we don't need to calculate the sum of the left part and right part using the for loop. We can use the accumulate prefix sum, right? And then we can further improve it by using the mathematical equation, right? To calculate the sum of any consecutive numbers, right? And Further, we improve it using binary search. That bring down the complexity to O log n. And then we try to solve this equation. Basically, we try to find out this using mathematics equations. And we find out x equals square root of x. And then we just calculate it. Okay? What have you learned? That's it.
Pivot.
Pivot. Is you can just.
What's the problem and what kind of algorithm have we learned?
Bruteforce.
What's the problem? First of all, what's the problem?
We have a list of numbers.
What's the this number? Come on, say more, please.
We have numbers and we
What numbers?
normal numbers.
Normal numbers. What's normal number? Can you give me an example? Like what are we trying
1,
to
2,
do?
3, 4, 5, 8, 7.
Yeah. What do you call these numbers? Nature numbers, right? If we have these nature numbers.
Natural.
Natural numbers. Yeah?
Natural is normal. Natural is a synonym for
Natural
normal.
numbers, natural positive integer, right? 1, 2, 3, 4, 5 till n. Find out if there's a pivot. Yeah, if there's a pivot integer, that the sum of the left part inclusive x is equals the sum of the right part inclusive x. Right? And what kind of algorithm have you learned today?
We learned about
Bruteforce.
Brute force, yes, we
Maths.
talked. And math and one more missing.
Numbers. You add.
How about the one you divide into two? What do you call it?
Binary.
Binary search, right? Binary search. Every time we cut it in half, right? And the last one is we solve it using the pure mathematics. Alright?
Yeah.
And the most efficient solution is using mathematics. Alright? And the first three approach are computer algorithm. The last one is more like mathematics thinking. Okay? Yes? Okay, that's it for today. Bye bye. Bye bye.